Thank you very much for the lively discussions during the break. It was very nice to be reminded how much easier everything is if you are actually able to see people in person. Nevertheless, I also checked the Discord channel, and it's even livelier. So please, if you're not there yet, join Discord, keep asking questions. We will basically use it here in the room as well. So if you want to pose a question to one of the speakers, feel free to do it there. It's my very, very great honor to introduce Wiro Niessen. He will kindly provide us with a keynote lecture for the MMIV conference. And I have this piece of paper in front of me that lists just his positions. And I will go through some of them. And there are so many additional information that is available in his talk. So he will mainly focus on things that is very close to every one of us. So he is the professor for biomedical image processing in the Department of Radiology and also in the Department of Medical Informatics. So it's a very dear colleague to a lot of us. This is in the Erasmus University Medical Center in Rotterdam. And he is also a professor at Delft University of Technology and there in the Faculty of Applied Sciences. Yale is on his list of institutions he has been before, and he's also the founder of a successful company, Quantib, and I think he will let us know about that endeavor in the talks. If you look at their website, they have exciting applications for brain, prostate, automatic segmentation, machine learning, and I'm very, very happy to have him here. I hope that the connection works and that everybody can ask questions in the presentation. Thank you very much. Wiro, are you available?
Yes, I am, if you can hear me well.
I can see you in life size. Please, I'm very happy that you're here. Start with your presentation.
Okay. Thank you very much. Thanks for the kind introduction. It's a pleasure. I'm gonna to present here. To start out, I'm also want to make just the disclaimer about that I'm also working with Quantib, still linked to the company for 1 day a week, but I will not be here to sell anything from the company. But I think just for transparency, it's good to mention it. I would like to share with you a little bit of the excitement of the potential of data science and AI, specifically to the field of medical imaging, but also beyond, using data in order to try to improve how we understand health and disease, how we can try to better diagnose disease and select better treatments. And I think there's quite a bit of opportunities there, but also some challenges. And I would like to address them in the talk today. So first, I think we see everywhere that data are becoming more and more important, and that data-driven technologies really have matured and are impacting all all domains. And I think in the health domain, on the scientific side, it is very much affected already, but actually in translating to clinical practice, there's still a lot we need to do. And I come from the field of medical imaging primarily, although increasingly I analyze medical image data in conjunction with other types of data, genetic data, personal data, data from clinical health records, even lifestyle data, in the health domain. But it's logical to do this presentation a little bit from the imaging domain, because obviously the breakthrough in machine learning and especially deep learning came from the field of imaging, not being medical imaging, but the field of computer vision. You of course all know the breakthrough and the paper in 2012 in which in the ImageNet competition in Stanford, in order to recognize objects in an image, this neural network outperformed all the competitors. Only actually you missed 2-3 minutes, so I want to make sure that I pick up at the right moment in the lecture. I'm not sure where I got disconnected, but I was explaining that the revolution for artificial intelligence came, of course, from this ImageNet competition, in which we saw that we could get very good performance of these algorithms in some sense in terms of recognition as good as human beings, and that has created enormous interest in this field. And we see by now that in many fields of computer vision and image analysis, deep learning based approaches are state of the art. And if we then start to think why this is the case, then we have to realize that it's on the one hand the availability of this large number of data sets, but they're also annotated. We have over 14 million images, and we also see that there are many categories that have been labeled. And the next important thing is that also this open challenge design, the fact that people can compete and objectively compare the performance of algorithms has been a major reason for the success. And I think in the medical domain, we can learn a lot from this open approach and this challenge aspect in order to really speed up progress in the field. So a question is, can the success of computer vision and data analysis and neural networks be translated to clinical practice? And I think the answer is yes, but there are challenges. So first, why is there so many opportunities? The reason is that not only are these algorithms very capable of performing specific image analysis tasks like performing image segmentation or image registration, which are the basis for a more objective, quantitative approach to radiology. But increasingly, if you think of a data science approach, you can try to relate image information directly to clinically relevant outcomes. You can predict whether you have a certain tumor subtype, or you can start to predict directly from the image data if a certain therapy is likely to be successful or not. And in this way, we are starting to utilize all the information in the data in order to get to clinically relevant outcomes that are relevant to the patient. So there's a lot of opportunities in this field. But there's also challenges. If you look at the specific health domain challenges, we need to do more than image perception. I think that data science and machine learning has falsely claimed that we were going to replace certain clinicians very soon. It was even stated that radiologists would be obsolete in a few number of years. But this is not doing justice to the enormous complex task of interpreting image data. I think the state of the art is that in perception tasks, these neural networks are very good, but in reasoning about image data, also in combination with other data, we have a long way to go to be competitive versus human intelligence. So I think in the coming years, we're more talking about how AI is going to assist human intelligence rather than replace it. But certain tasks for sure will be automated. Then second, it is not as easy in the medical domain to collect data as for a challenge as had the ImageNet challenge by Stanford. It's not just about collecting images and a binary label. Typically, image data are combined with other types of information in order to do a diagnosis. And also the context in which data have been acquired is very important. It makes it different if you have an MR image of the brain and you have complaints or you do not. It makes it different if you go for a first consult or whether you've been sent to a specialized hospital because you are already in the system. So in order to really develop diagnostic and prognostic algorithms, we have to collect all this type of information. And this is a hard, tedious job to do, and getting good access to data is an enormous challenge. Then human biology and pathology is highly variable. If certain diseases only strike once in 30 or 50,000 cases, even a data set of 20,000 patients is a small one, and typically we have smaller data sets. And then finally, we know by all learning algorithms, it is important on what data you train, and we now really don't have training data that are really resembling the world's population. Most of the data sets are focused on Western countries, so there's a lot of, or also some large Asian collections, but data bias is a challenge in our field. But still, I think, yeah, and you can see the problem with data and bias, for example, in literature as well. This is a very nice article that appeared about 1.5 years ago by DeepMind in Nature, in which they predicted acute kidney injury up to 2 days. And if you would read the popular literature or the popular press, you would think that tomorrow this would be implemented in clinical practice. But if you really dive into it, you would actually see that because this is a retrospective data set on which an algorithm was built, and this was a very biased data set in the sense that it was from the US Veterans Hospital, so all people that have served in the army can get their medical care through a whole chain of veterans hospitals in the US, and they have a common data set, so you can really develop algorithms on a large data set, but obviously this is a very biased population, and the extent to which such algorithms generalize to other settings is very questionable. So that really is still a hurdle to tackle. So our own research is therefore often in the case of much more controlled data setting, in which we have clear control of the quality of the data. So one of the areas in which we develop our AI tools is in the context of a population study. It's a study that we already run over 25 years in the city of Rotterdam. We include people 45 years and older, and there's extensive genome and phenotyping imaging data available. And the idea here is that we try to understand better why some people stay healthy and other people develop disease. Here you see the design of such a population imaging study. What you typically do is you try to first collect as much risk factors as you can, information of which you think it may be predictive of a healthy life or the onset of a disease. And then we talk about, for example, genetic data, but also environmental data and data about your lifestyle. And then you follow people over many years and you just look for the occurrence of events happening in life, whether people get cognitive decline and develop dementia, or whether they're struck by a stroke. And then the idea is, can we say something about the relationship between risk factors and outcomes? Now, this is just an association, if we find it, and a black box because of that reason. But if we start to do imaging in between, then actually we can start to relate risk factors to changes that happen in the brain, and we can link changes in the brain to clinically relevant outcomes. Or we can combine, for example, genetic data and imaging data to predict outcomes. And then these things become more of a data science approach. Now, a question you may have is whether this approach is going to succeed. Is it likely that somehow we can get information from image data that can predict why a certain person has more chance to get cognitive decline or dementia? Now, this is a very nice study that illustrates that this is a useful avenue to investigate. It's a study in which we took images 3 to 4 years apart, in which you see white matter hyperintensities. These are mainly white matter lesions, and they're linked to diseases, neurodegenerative disease processes in the brain. So if you see more of these white matter hyperintensities, you see there's more disease load, and these white matter lesions have been associated with an increased risk of stroke and dementia. And the two images you see here are from the same person, but about 3 to 4 years apart. And we took thousands of those 1,000 subjects on which we took these images. And what we did next is we utilized image analysis approaches in order to compare the two images. So we registered the first time frame to the second scan 3-4 years later. We automatically segmented the white matter lesions, and then we divided the region of the brain into 4 regions. Those regions in which the white matter appeared healthy both at baseline and follow-up, those regions in which the white matter lesions had grown, and those regions in which once white matter lesions were appearing. And then we started to look at all other MRI sequences to see whether there was a statistically significant difference between those regions. So here you see the statistics of one parameter, the fractional anisotropy. You can derive it from diffusion MRI, and this parameter is linked to the microstructural integrity of the brain. And there have been numerous studies that have shown that this parameter is linked to the process of neurodegeneration. And if we look at the different regions, then we see that at baseline, when we don't see a white matter lesion, but in a region where later on a white matter lesion appears, that this fractional anisotropy is already statistically significantly different in those regions. So before you start to see pathologies that are now used by a radiologist to diagnose a patient, there is already a signal in other MR imaging that we're not currently using diagnostically. So we're underusing the information and imaging data with the current paradigm. And that's not so strange, because if you think about it, we collect a lot of information on the function and the anatomy of the brain, but we let one observer look at it, interpret the data, we see some atrophy, etc. So we reduce all that information from the image into a number of descriptors, and those descriptors are weighted with other diagnostic information to make a diagnosis. So we think it's wise to look at next steps and start to do smarter things, because we see there's a lot of subclinical disease that we're not looking at this moment. And in this way, we started to organize the work in our hospital a little bit as a data science engine. We collect information. We do this in this Rotterdam scan study, but we also do it in our clinical studies. And we try to collect as much as possible information from these images, and we derive a large number of features of these images, and we try to estimate with machine learning techniques which combination of features may be predictive for the onset of dementia, for example. Now, this work has really been sped up by deep learning. As an example, one of the things we do with our data is that we extract the white matter pathways, and it used to be an algorithm in which we combined an approach which is called fiber tracking on the diffusion tensor data with an atlas-based segmentation. And this way we had an automated algorithm that took hours to compute for one single image the white matter pathways of the brain. Because we did this for about 10,000 scans in the Rotterdam study, we could design a neural network to perform the same, directly linking the diffusion tensor data to segmenting the white matter neural tracts. And the same process we can now do with the same accuracy in half a second. This just shows also in computation of biomarkers how disruptive this deep learning technology has been in the field of medical image analysis. Now, this is one of the disclaimer slides, just to show that in the end, we want to bring these kind of technologies to the patient. We don't do it from the academic setting. So some of the work we do, especially in quantifying aspects of the brain and computing that in a population study like the Rotterdam study, provides us a means to have a report in clinical setting in which we have a quantitative report in which imaging measures are compared to a reference population. And this is very normal in a lot of areas of medicine. If you look at blood pressure or your height or weight, there's reference curves of the population, and clinicians use those reference curves to interpret your data. In imaging, that's much less common, but we think that with these kind of technologies, in order to quantify aspects of the brain and linking that to reference data, we can also make the field of radiology more objective and quantitative. But we can do much more, and this is quite kind of an interesting approach to take, is that you can also think of totally new imaging biomarkers. Here we train a neural network to predict someone's age. Because we have thousands of MR brain images, and we know the age of participants in the Rotterdam study, we can make a neural network that just based on the image of the brain predicts someone's age. And this is logical because if you think about getting older, we know that the ventricles grow because your brain shrink. So there's changes in the brain that could be used to estimate one's age. And we found that we can do this, and we can do this with an accuracy of about 4 years. So we have a population between 45 and 90, and our neural network, if you give it an MR brain scan, it can predict someone's age with an accuracy of about 4 years. Now, you may think that's not very accurate, but what we actually think is that we're actually seeing that some people have an older brain, probably because of genetic factors or lifestyle. We also know that some people stay cognitively better, have a better shape. And therefore, we started to develop a new biomarker, which is the difference between the biological brain age that our neural network predicts and the calendar age. And then we checked whether people develop dementia. And we saw for those people, that's the red line in this graph, those people in which you see that they have a positive biomarker in the terms that their brain looks younger on average than their calendar age, they actually, after 10 years follow-up, are longer dementia-free. So this seems to be a biomarker that we developed in this way. So if we go on, then there is we see that this is something we're not only using in the field of neurology, also in oncology, we start to derive more and more information from image data to get better diagnostic and prognostic classifiers. Here, the idea is that patterns in the image somehow relate to the presence or state of disease. So also in the oncology domain, we have started to develop these data science engines in which often in a multi-center setting, we collect many, many data linked to a certain type of cancer. We compute multiple features, and then we use machine learning in order to see whether we can predict, for example, a substatus of a tumor. So here's an example, low-grade gliomas. This is a tumor in the brain, and we know that there's a genetic subtype, and if you have that genetic subtype, you have a better prognosis. And especially older patients with this subtype, you may not want to perform a surgery or a biopsy. The ground truth to determine the mutation is to do a biopsy. So we checked whether we could, based purely on MR imaging data and such a data science approach, do a classification. And again, this utilizes the same framework, extracting a number of features and linking the features to the outcome. And then you actually see that these are the types of tasks that in the coming years we see that algorithms are going to be introduced and used a lot because you can really reach the performance of expert radiologists in this type of recognition tasks. So I now want to make a small step towards going beyond imaging. If we think beyond imaging, one important field is genetics. And in genetics, we also see that on the one hand, we learn a lot. On the other hand, it's very difficult to bring genetics to individual prediction. And here is a graph that exemplifies the enormous complexity here. What you're seeing here is genetic variations. You measure them as SNPs, so it's variations on the human genome that occur in the population. So as an individual at a certain location, you may have one or the other variant. And these, here you see the 29 variants on the human genome that have been linked to give a statistically significant increase in the chance of Alzheimer's disease. But it's 29, and most of them only give you a very small additional chance, and they're also very common in the population. So most of these SNPs are in 20 to 50% of the population and only increase your chance to get Alzheimer with 1%, which means that it's very difficult, even with this knowledge, to build an individual risk model. Now, the combination of image analysis and genetics can start to help here. First, it's quite interesting to link genetic data not to disease, but to image data. We have used this at a large scale, a lot of studies in which we looked whether there are certain genetic locations on the human genome that code for changes in the brain that link to Alzheimer's disease. For example, we have found new genetic loci that determine hippocampal volume, and we know that a smaller hippocampal volume is associated with an increased risk of dementia. But what we also did, we also started to visualize in the brain what is the difference between subjects that have a genetic variant and who do not have that variant. So what you see here, it's sort of a library, and we have supplied this library to people that are interested in neurosciences and in Alzheimer's disease. And what we're visualizing here is where there's morphological changes in the brain between subjects that have or have not a certain genetic variant that is associated with an increased risk of Alzheimer's disease. So what this provides is that the genetic analysis provides you an association. You know, apparently, this location on the human genome, what kind of genetic variant you have there, determines an increased risk of Alzheimer's. But this is also affecting the structure or the function of the brain here. So maybe it's a process in this region. So this starts to provide insight on top of genetic data. But we can go one step further, and that's the link I wanted to make with AI. So whereas images lend themselves very much to AI because the process of a neural network of convolution is very natural to images, you can think the same way of genetic data. If we think of our human genome, our genetic code codes for different genes. Genes make proteins. Proteins take place in processes of the in the body, and eventually they lead to normal growth, getting older, certain pathways. So what we start to experiment with is making topologies like neural networks with a lot of connections, and prior knowledge about how genes code for proteins, how proteins take place in certain disease pathways is encoded in these networks. And then we do a similar optimization as with imaging, in the sense that we try to optimize the weights in order, based on a learning set, link genetic data to prediction. For example, we start to predict the chances to get schizophrenia this way. And we see that this type of analysis is much more powerful than the normal, massively linear statistics that is used in most of the genetic literature. So we think this is a very exciting avenue of research. The holy grail, one of the holy grails in the life sciences, is to get a better grip in how your genetic liability with your lifestyle and environmental factors defines the phenotype, what you look like, whether you get a disease or not. And so far, this research has been primarily based on this massively linear relationships. But wouldn't it be great if we start to leverage the power of deep learning algorithms to find much more complex relations and provide more insight? And the interesting thing is actually, even though people call deep learning a black box, once you do this, you can start to visualize which part of the network is relevant for the prediction, and you can actually learn something and find out what proteins or what genes are relevant in order to predict disease. So this is a very exciting area. I think there's some time left. I just want to spend a little bit time about the essence of bringing these technologies into the clinic and what we have to do. So I think we all agree on the potential of these technologies, but we also see that actually translating them to clinical practice is hard. And first of all, it's because algorithms are sometimes trained in a too limited scope and they don't generalize well, or we don't know how well they work because the validation is not very clear, or they just perform a subtask and they're not optimized in the clinical workflow. So we really need to do a better job of, on the one hand, defining the proper use cases for AI, and on the other hand, developing them such that they are generalizable to many settings and that we know how accurate they are. And this really requires a health data infrastructure. And come back to the ImageNet challenge, we have to do a better job of making data available both for development but also for validation of novel algorithms. So in the Netherlands, we try to do that by building a health data infrastructure. And the backbone of such a health data infrastructure is that locally people have to ensure that data are collected fair, such that they adhere to international standards and that data become findable, accessible, interoperable, and reusable. Ideally, data should become machine readable, such that you can send algorithms to the data. So we start to pilot with experiments where we put data in different hospitals and ensure that we can send the code to the different hospitals to optimize algorithms over many hospitals. And then the second thing is about the validation. And computer vision, I think that they have done a good job for many years to really do challenges. In our field, we also started to do that since 2007 in MICI. We have challenges and we start to objectively compare algorithms. But I think most of these algorithms are sometimes defined by people that develop algorithms. And I think they should ideally be defined by clinicians that know for what tasks they would need AI. So we've set up now a collaboration between the MICI community, the American College of Radiology, the RSNA, and the ESR, where we collaborate in the sense that the clinicians provide use cases indicating this is the typical data we have, this is the type of information we would like to get. And then we build challenges around it to enable the objective comparison of the performance of algorithms. And I hope that this endeavor will also lead to more sites being able to provide their data to support these kind of challenges. Now, as a final takeaway, I would like to see that I really dislike not being able to go to Bergen. It's a beautiful, Norway is a beautiful country, and especially the fjords and all the regions. That would have been great to be there. And we all know that we are doing this in a hybrid fashion with most people online because of COVID. But I do think actually COVID is also has opened our eyes that we have to do a better job in the biomedical domain to learn from our data. There's so much potential in data science and AI methods that we must do better. And at least in the Dutch situation, we have been confronted with our inability to learn quickly from data that we collect from COVID patients. And because of that, a number of initiatives have started, and they're speeding up, setting up infrastructures for reuse of data. So first of all, there's a lot of international initiatives that try to harmonize the data collection at the source so that data of COVID patients can be reused. And in the Netherlands, so I'm so apologize, part of this slide is in Dutch, but the idea here is that you see a data portal that would enable researchers in the Netherlands to search over multiple hospitals, what lab data, image data, and clinical data are available. So we start to locally have better data stewardship, adhere to FAIR principles, and make data available. Then local data can be made, you can inform the portal what kind of data is there, and then you have a catalog, and researchers can search for the data and request the data for their research. And we see all kinds of hurdles with the imaging data. We're setting up an imaging database of CT and thorax images are being taken because of the pressure of wanting to learn from COVID patients. So I think the future of health is data-driven. We have a lot of data. As a person, I would like to have access to my data. I would like to be able to tell whether my data can be reused for research and innovation. And I hope, because we all are going to do it, we're going to build better models to predict whether I'm at increased risk of disease or what treatment is best for me. This will require collecting data and pooling them across the life cycle. In order to really profit from them, we need infrastructures to make these data accessible. This is an enormous effort, and we have to align multiple stakeholders in this effort. But if we do so, really, we can get novel insights and higher quality algorithms because of the enormous potential of data science. So I think the future of our healthcare system is a learning healthcare system, but we in certain areas have to get our act together. We really have to work on better access to high quality data. We have to implement prospectively that data are collected fair, and we have to adhere to the principles of open science. Also, in evaluating and validating, we have to go for the competition aspect and really objectively compare algorithms. And if we do so, we will have a flux of a lot of interesting algorithms with potential that we can then test prospectively for the responsible introduction of AI. Because at the moment, most of the things we see have only been validated in a retrospective setting, and we have to go to the prospective settings to really prove the value of AI. With this, I would like to thank you, and if there's questions, I'm happy to address them.
Thank you very much, Wiro. That was a very enlightening talk. We had many questions in the discussion round, and I personally started to write down, just like every second slide, I had a different question. I can only ask one, so it's one from the very first. So the excitement that you said, and your experience as a past president of MICAI, you know that there is a lot of researchers that create very intelligent models, and then there are a lot of very excited users in the clinic who would like to use them. So is there a way for these tools to become more interactive? We know that the limits of a tool, it's usually easiest explored if you can play with it. And right now it always looks like this black box solution that comes out, but there is no interaction. So is there like a kind of a dialogue that can be established with the AI to teach somebody who is in radiology when the system actually fails and when not?
Yeah, I think there's a very interesting and good suggestions. Indeed, we do things very static in terms of you have a given data set to train on, and then you validate, and then you know how well it works, and then you throw it over the wall and you want other people to use it. Also because of the regulatory bodies, if something is FDA approved or CE marked, it needs to be fixed. Whereas what we need is a more dynamic way of optimizing models and understanding how they work, like a sandbox models. So I think the idea of starting to iteratively improve these algorithms with a set of users, and also we also see that there may be relevant bias. It may be that certain subtypes of in certain regions you would like to optimize the algorithms in a certain setting. In that case, you would like to be able to modify the training set and the validation set. So I think like paradigms for dynamic deep learning or continuous learning, in which there's a much more interaction between developers and end users and new data, is a good direction to go.
Yeah, we have some more questions. Nushka is here to share those with us. Thank you for helping out.
Yeah, we have many questions on the Discord, and many of them are long ones, so forgive me if I make a mistake while reading them out. So first we have Helvik Haaland. He says, many thanks first for a great talk, Wiro. Then I'm curious, how deep did you look into the bias question? One could also turn the question around. Instead of getting rid of bias, which maybe never is possible after all, one could try to learn how to best cope with it, after having studied in depth what type of bias is present. With your great Rotterdam study, you have amazingly valuable data, but sure not without bias. Is there a smart way to exploit this data bias aware?
Yeah, it's a good point. So in one way, we would like an algorithm to get the unbiased data that are representative for all situations, and then hope that the model can cope with it. But we also see if we limit the training set to a certain scope, the performance within that setting becomes better. So an alternative is indeed also to say, okay, we tailor the algorithm to a specific situation. And I think this is an unanswered question. I think we're in almost all cases, we are in the domain of having limited data in view of the heterogeneity of disease, difference in people. So perhaps we have to locally optimize algorithms. But I struggle a little bit myself with that concept, because what about guidelines? You know, how are you, if your AI algorithms is different here than there, can you really come up with threshold values when to operate people or not? It is really a difficult one, and I think we need a lot of research to understand what is the best trade-off here.
Thank you. Then we have another question from Pierre Gianluca. Thank you for a brilliant, comprehensive talk. The final purpose of a clinician is not a simple classification, but to choose a course of action, different treatments, etc. The choice is made using rational decision theory, otherwise there's mathematically guaranteed loss. So the clinician needs probabilities besides labels. How is the progress in outputting probabilities and well-calibrated ones?
Yeah, so this is often possible. Often in case there is a final segmentation or a classification, actually the less layers of the network can often be interpreted as a threshold or whatever. And if you leave that out, you can come up with an ordinary scale or something between 0 and 1. So I indeed think on the level of the multidisciplinary board, where a lot of these decisions are made, a lot of information is combined, I think the initial algorithms are going to be trained not on all the information. And indeed, the outcome of algorithms is going to be combined with information from other sectors where there may also be algorithms or not. I mean, we will for a long time be in the hybrid situation that some of the data is quantitative and AI supported, and another part of the data is going to be still subjective. And then in order to combine that information, it's nice that you don't threshold too much, but you provide some kind of both a value between, say, 0 and 1, plus also some confidence interval. Often we also can try to provide a confidence interval with our estimate. Would also help the final decision.
Thank you. Then another question from Erlin. Traditional predictive models, linear regression, logistic regression, etc., have failed to be used as reliable explanatory models in terms of causative factors in medicine. For example, how do lifestyle factors affect disease? Even if we can partially compensate by adding known covariates into the model, we cannot account for all unknown covariates. As a result, the highest standard still remains a placebo-controlled randomized double-blind study. Do you think there's a reason for excitement that new machine learning models and explainable AI can perform better in presenting causative factors than traditional predictive models?
Yeah, so this is a very interesting question, and I'm not sure if I'm even up to date with the state of the art in causal machine learning and finding it out. I think it's very difficult to really, for a hard proof of causal relationship, to go away from a prospective randomized clinical trial. But I think, we can come a long way with coming up with plausible explanations, and but it remains. So I remain to be convinced that you can do it without a prospective randomized clinical trial. I've seen some presentations on causal machine learning. I'm still struggling with understanding whether you can really, from this data, which you're still associating input with output, even though whether you could do it without. I think we will still do prospective studies also with AI methods if we want to integrate them. But maybe I'm missing, and I have to understand better what people are doing in the causal machine learning field.
All right, thank you. Then one last question from the Discord from Anders Rudel, tuning in from Denmark. Between us, actually, Norway, Netherlands, Denmark, right? So he asks, first he says, thank you for a very inspiring talk. The phenotypic effect of genes are linked to how the genes were applied and used during the lifetime of the organism we are imaging. Could you use longitudinal databases for exploring this and perhaps gain a better grip on the genetic factors than we have done so far?
Yeah, I think that's a very, very interesting one. But in general, the large studies are not so long. So we have a relatively long study. So we've already been collecting data for 15 or 20 years. But for a lot of our analyses, the Rotterdam study is not enough. And we need to go to other repositories. UK Biobank is a great one. But imaging in UK Biobank only started a few years ago. So what we see, whereas this is true, in an individual subject, on a large scale, to have many years of follow-up, we still lack those data. Sometimes you can also think of combining studies. If you would like to do a live course approach, but waiting 80 years for a subject to collect data is difficult. So you may also try to infer some relationships by combining cohorts, young cohorts with middle-aged cohort with older cohorts. But of course, you have some methodological challenges to do so. But indeed, you have to address this as a live course issue, and it's the exposure over time. So yes, but the number of data quickly decreases if your question becomes bigger and goes over more years. And
yeah. Thank you very much, Wiro, for a very inspiring presentation and also for this very nice discussion. Hauke, would you like to close the session or no? It's me closing. He's already removed his microphone and is ready to leave, maybe. So, you have another talk coming up. Yeah, he'll be back, don't worry. So, with this, I would like to thank Wiro very much, also from you, from the audience. And then we welcome Alexander Ludnervold to the stage for the next session.